Yep. You guys doing all right? I mean, really, are you doing okay? So. Yeah, I know.
2020.
Relatively. Huh? 2020, okay, yeah, exactly. That's going to be a thing. I'm going to make that a thing for next year. I saw a shirt that said, first rule of 2021 is don't talk about 2020. And I'm like, that's going to be another good thing. We just don't talk about that year. We'll see. November might still make it a good year. We'll find out. That's all I'll say. All right. So no questions from anything? No questions from any homework?
A quick question about
Yes.
About the z-score chart. It was something that was kind of weird. I don't know if I'm looking at it wrong, but if you go to the z-chart and you scroll to the very bottom of the positive z-scores, you know how it gives us that little shortcut where it shows the confidence level and then the critical value. So for some reason I'm looking at it and the confidence level 0.90 says that the critical value is 1.645.
Totally.
But then if you look to the left, it says that 0.95, it has a z-score of 1.645. Am I just...
Totally. I love it. Okay, you ready? Here we go. And you're all like, all right, dude, get all happy about my confusion. But no, I'm happy that you're asking this question. I love it. You got to pay attention. And if something don't make sense, ask a question. Shit. So if I look up 1.645 in the z-score chart. Oh, sorry. Thank you. I always forget about that. If I look up 1.645 in the z-score chart, it will tell me this whole area, right? And that is 0.95. Now stay with me now. This is a really cool connection to make. What area is here then?
0.05.
Yes. All right. Now stay with me. A 90% confidence interval is this area, not this area. It's this area.
Okay.
And I really want you to see this. What area is out here then? On either side.
0.05.
So won't this be the same z-score? Yeah. So the z-score that has 95% below it also happens to be the z-score that contains the middle 90%, because that's still 95% there. So be very careful. The z-score chart tells you the area below a z-score. Confidence intervals are not areas below, they're areas between. So they're not gonna jive, they're not gonna match up.
Got it.
Does that make any sense to people?
It does, yeah. Thank you. Thanks for...
Okay. So the little baby chart is specifically for confidence intervals. And the little thing on the other side is specific z-scores in their areas below them. Yeah. I like it. Good question. Anything else, guys? From anything, homework, quiz?
I had a question on 8.1 homework.
All right.
For numbers 10 through 12, can you just help with one of those? I was having kind of some trouble understanding the problem.
Oh yeah, so these get very funky, just to use a term. Let's see. Yeah, these are a little bit interesting. You can look at them from a purely mathematical standpoint if you want to. So these questions here, right? If the census wants to increase its level of confidence and keep the error bound the same by taking another survey, what change should it make? So it wants to keep the error the same, but increase how confident they are. So you can look at that mathematically. So let me say this again, just to get everybody in the right frame of mind. This wants me to keep the error the same, but it wants to increase how confident I am that my interval catches something. So there's something I can change to make that happen. So let me go to the board again. Go away. We look at the formula. Holy crap. Do something with you. All right. Here's the error. If I want this to stay the same, but I want to increase the level of confidence, which means my z-score would actually go up. I think we talked about this before. This is a little bit weird. Then what has to happen to this? If my z-score goes up, but I want this to stay the same mathematically. So if I have 10 times 2 divided by 10, right? Something times something divided by something. If I make this go up to 20, what has this got to do so that overall it's the same number? Does that make sense? Right now, this is the number 2. If I make that 20, what does this have to be so it's still 2? This has to go up. So from a mathematical standpoint, if I want my confidence to increase, which means this goes up, then my sample size has to increase. From a less mathematical standpoint, from a purely conceptual standpoint, yes, survey more people, exactly. If you just say, all right, I want the error to stay the same, but I want to be more confident. What do you do in statistics to be more confident about what you find? You take more, right? You take a larger sample. Taking a larger sample will always increase how confident you are with what you find. That kind of makes sense. If I talk to 5 dentists, I'm not going to be very confident about what gum they like. If I've talked to 500 dentists, now I feel pretty confident about reporting that data. Does that make sense? I mean, so that's one of them. And the other ones are sort of the same. You can kind of either reason them purely mathematically, or you can reason them out conceptually. So it's up to you. Hopefully one of those ways makes sense. Okay. Anything else, guys? Either from the quiz is all graded, or from homework. You guys are good? Okay, all right. So, all right, we're gonna get back into where we left off, just to kind of catch us up to where we got to. I don't think we finished that handout out, did we? That handout. So let me open this up here. Let me remind you that handout we were working on last time. Give me a minute. I forgot to get it ready. Where'd you go? There you are. All right, let me move all of you over there. Bam. So this is what we did last time. Schmack. Remember the dolphins and all that kind of stuff? Dolphins. And we did all this and we did all this. And then I went to the board and I created another confidence interval formula. These formulas all have very similar looks. They're a sample something, give or take z times a spread. And the only times you're going to use these formulas, the x bar plus or minus, or the p hat plus or minus, is if I ask you to make a confidence interval. Never use it otherwise. Some people like to use this formula everywhere, and I don't understand that. All right. So let's try this problem out kind of together. Oh, I got to get this guy back up here. Get over here. Can somebody remind me, do you guys remember what p hat stands for? What's that p hat symbol mean?
Sample percentage?
Yeah, it's the sample percent. I like it. So what do you see in the sample that would lead me to a percentage? And in fact, I kind of give you the formula, but what would those things be? What's N?
652.
652. And out of those, I saw how many successes?
459.
459.
I like it. And definitely voting. Let me make a really cheesy, you want a really cheesy public service? Voting is a success, kids. So be a success. All right. So 459 out of 652. And what do you get when you divide that bad boy?
About 70%.
Yeah, and here's where we're going to have to be a little more specific. The only thing that I let you take to just 2 decimal places is really a z-score. This has got to be at least 3 decimal places for p hat and q hat. So remember what I said about 7.8 billion years ago? I said if you take everything to 4 places, you're covered. Z-score, you have to round it to 2 because the chart only goes to 2 places. And if any of you are still using functions in the calculator to get your areas, stop. You know who you are. Stop. Now, is this cool? So that means that I saw just over 70% of my sample voted in the last, said they voted in the last election. I'll say it like that. So then what must Q hat be? Uh-oh.
0.296.
Yeah, no matter if they are wearing hats or not, whatever clothing they're wearing, P and Q always make 1. So 1 minus 0.704 is 0.296. I like it. So right now, my best guess for the true percentage of people that voted is 70.4%. That's my best guess. But just saying that to somebody doesn't give them an idea of how confident I am with that. So creating a confidence interval, kind of, you can tell by the name, is a way to communicate that idea to somebody. So N we already know is 652, right? Now, here's where things get really, really interesting. All right. I always forget to talk about this before I jump into this. So I'm going to stop sharing for a bit. We got to check about what the shit this means. What the shit? So let me see if I can find this handout. Hold on. Should I try to find this handout? No, I'm going to do it up on the board. Do it live. So, in fact, I don't even know if I did this handout with you guys. I might not have. Let me ask you this. So this is all a side note, really. All right. If I have, let's say, N is, what do you got? 50. And P is 0.5. What's the mean for that situation?
25.
Yeah, half of 50, 25. So if I were to calculate the probability of 0 and the probability of 1 and blah, 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 all the way up to 50, and then plot those, at 25 would be the tallest bar. And then it would go down from there in both directions. Probably faster than actually, but oh well. And forever. Both right. Let me stop for a minute. Are you guys semi with me? The mean is the expected value. So it's going to be close to, or if not the tallest bar. So the minute you go away from the mean, it's going to be smaller probability. Just to get a feel for that and for a beautiful little review, How do I get the probability of 25? What's Q? Q, boringly enough, is
0.5.
0.5. I love it. I love it. I love it. Stay with me now. So the probability of 25 would be N choose X. So 50 choose 25. You guys remember this business? 0.5 to the 25 and then 0.5 to the 25. So somebody do that for me. And while you're doing that, I also want to know the probability of 24, just to show that it's a little bit shorter. So this would be 50 choose 24, 0.5 to the 24, 0.5 to the 26. So somebody do those for me. Where's my calculator? I'll do it with you guys. Okay, cool. Has anyone got, let me see, survey more, oh, I'm sorry, that's from Merlin. Anybody have this one? The probability of 25?
0.0561.
No.
I
Did
got
I do some-
1122.
Yeah, 1122. 23 really, but that's right. And then what about this guy, probability of 24? So I got this. You guys with me out there? All right, I got one person with me. Okay. Two people. All right, sweet. All right. And if you did the probability of 26, you would get the exact same amount as this. If you don't believe me, do it. Did the probability of 26, you would get this same thing. So it starts high in the middle and it goes low from there and it goes low from there. So that looks like it's roughly what?
Normal.
Normal, yeah. Okay, now, what is this wall here? What is the lowest you could get? What's the lowest amount you could get? What's the lowest number you can get?
0.
0. So there's a wall here, right? And there's also a wall up here because the highest number you can get is freaking 50, right? Are you guys with me? So it kind of makes sense if the percentage, if the probability of success is 50%, the highest bar will be right in the middle. Doesn't it have room then to go down from there on both sides? So now what about this? Stay with me. Let me arrange some things here. It's driving me crazy. All right. So what if instead, can you guys still see this yet? What if N is 50 and P is 0.01? What's the mean then? What's the mean if N is 50 and P is 0.01?
0.5.
Yeah, so you just do 50 times 0.01, 0.5. Yeah. So stay with me, stay with me, stay with me. Where would the tallest bar be now? It would be like right next to 0, wouldn't it? Because the mean is 0.5. It would be like right here. Then it could only go down from there then. I really want you guys with me. So the fact that this mean was in the middle meant that there was room for it to go up and then room for it to come back down. So then it looks normal. It looks approximately normal. If the mean is too small, then the tallest bar is in the wrong place. It's way the shit over here. There's only room for it to go down. That doesn't look normal at all. So I need in order for a binomial to be normal, approximately normal, I need the mean somewhere in the middle here so that it has room to go up and then room to come back down. So here's how that translates. So what we're doing right now is for means, I know what the check is. What have we checked when I take a sample and talk about the means? What do we check to make sure that it's normal enough?
Just the sample size so far?
If the sample size is bigger than
30.
30, kick ass. So what we're doing right now is we are developing a check for percentages to see if they're normal enough. So here's what we got. The mean has got to be in the middle somewhere. So what that means, and again, the reason it's the specific number is a little bit beyond the math of this class. But the idea of it, so the mean is NP, right? That mean has got to be at least 5. If it's at least 5, so if it's not 0, if it's at least 5, then it's got some room to go down and room to go down over here. Then it's got room to look normal. So it's not slammed up against this wall. Now, at the same time, you have the other wall to worry about. And what's really kind of nice is, let me see if you guys are cool with this, the number of failures. The average failures can't be too big, too small either. So these, I always think of this as this wall and this as this wall. It tries to pull it away from both of the walls. I really want this to make sense. Because again, I keep redrawing this. I know, it's too bad. If I put my wall there, it's got no chance. If I put my highest bar against that wall, it's got no chance to look normal. It's got to be somewhere in the middle, and that's what these two do. It makes the highest bar in the middle somewhere. Let me stop talking for a minute. It's a little weird. So if I have a percentage problem, how do I tell it's normal enough? I check these two things. Instead of n greater than 30, that's for means. If I have a percentage problem, I must check these things. If these are true, then it's normal enough. So let's go back to the worksheet, unless there's any questions. I'm sure you're like, I don't even know what to ask. Yes, go ahead.
Where did you get the 5 from?
See, that's... Do you agree the idea is to pull it from that wall, right? To pull it away from the wall?
Right.
The idea makes sense. Why is it 5? It sort of goes back to why is it 30? Why was it 30? It's the same answer, to be honest. And I love it. You guys are like, we don't know. Shit. Did we not ask? Everybody? Guys, did we forget to ask about that shit back when we did it? Yeah, shit. They're sort of the same reason. If we run a lot of simulations, then making these bigger than 5 ends up making the thing actually normal enough, no matter what it started off as. Same thing with n greater than 30. We said, okay, 20 makes some of them good, but not all of them. 30 is about where everybody starts to look normal, no matter how funky you look to begin with. That's why 30's. Go ahead, sorry.
What if n doesn't go past 5?
Oh, then you're stuck. Can't do shit. Is that the question? It's sort of like if you don't take a large enough sample and you don't know what the distribution of the population looks like, you can't do shit. At least not in stats 1, which is where
It's
we
just
all
too
are.
small of a sample?
Yep.
Okay.
Yep. I like it. All right.
So,
All right. Go
so
ahead.
if you were to put that on a test and the sample size was too small, would you say the sample size is too small so you can't do anything with this?
Well, if it's a percentage problem, you don't look at the sample size necessarily. You look at the results of these two things, right? So if either one of these is less than 5, then it's not normal enough and you can't do anything.
Okay.
Okay. So let's come back to this. Come here, chair. I got to get to my office and get my nice freaking chair someday. All right. Oh shit, where are you? Oh yeah. You pull you guys back over here. So that's what I mean on this handout when I say check NP. Oh, so now that we're back to this, stay with me. The whole point of making a confidence interval for the proportion or the percentage is because I don't know what P actually is. What does the symbol P represent in this type of problem? So to, run it up against what P hat is. P hat is a sample percentage. So what's P?
Population
The
percent.
population percentage.
I love it. So P is what I'm trying to estimate. So do we know what that is? We don't have a freaking clue. So if I'm supposed to check NP and NQ and we don't know what they are, what's the next best thing to use? Freaking P hat and Q hat. That's my best guess. So it's still the same idea. I just don't know what the hell P is. So I'm going to use the P hat and the Q hat. That's my best guess. So what do we get when we do N times P hat? What do we get when we do 652 times 0.704?
459.008.
Yeah, and I want you guys to realize, is anyone surprised that it came out to be 459? 459? See up here? I want some of you to understand what I'm about to say, because it's really kind of, it's a quick little thing. What was P hat? P hat is the successes divided by N. So what is N times P hat? It equals the successes. So I can just look at that number. That's what N times P hat is. If you don't like that, then just freaking do N times P hat. Who cares? You'll get the same answer. That is at least 5. Check. So what about N times Q hat?
192.992.
192.992. Yeah, and that's at least 5. Check. So what does that mean? Those two are checks. We're dealing with a what? What does that mean?
Normal enough.
Normal enough. So it means the exact same thing as N greater than 30 for means problems, right? That's just what it looks like for percentage problems. You got to check this. All right. You guys love that.
Quick question.
Oh, go ahead.
How'd you get Q hat again? Sorry.
Oh, so like I said, we knew that if P was 0.7, for example, Q had to be 0.3 because together they make 1. Is that cool?
Oh, okay, got it. Yes.
So then I said, no matter what clothing they're wearing, hats or socks or whatever, there's no P sock, thankfully. P hat's bad enough. It's the hat you don't want to wear. But whatever they're wearing, they have to still make 1. Yeah, I like it.
Okay, thank you.
You're welcome. All right, let me see. I got all kinds of extra. Oh, Jeff, are you kidding me, Jeff? What all did I just write? Oh, not too much. Let me clear what I just wrote because I used the wrong thing. I love it, Jeff. You are awesome. So let me put this back in. 652, 296. That was what, 190 something? Can't remember now.
192.
3.992.
192.992.
Oh, 182. I don't care. It's bigger than or equal to 5. That's what matters. All right. So what do we know for this formula? We definitely have the P and the Q and the N. So the only thing I don't know at the moment is Z. How do I figure out what the Z is going to be? How
Use the Z-score
confident do
chart.
I? Yeah. How I want to be 96% confident. Why am I allowed to use the Z-score chart? Because these checked out. If these didn't check out, I couldn't do this problem. So now I say 96% confident, right? So I want to be 96% confident. You got to go back to the old way of doing this. You can't use the little baby chart. Too bad. So let me see. Do I have? No. Let me see. So what am I going to look up in the z-score chart? Shit, stop it. All right. What's this area out here?
0.02.
Man, Jeff, will you stop doing that? Sorry. I don't know what's up with today. Is this the way it's going to go today? Yeah, so this area here is 0.02 because there's 4% total outside because there's 96% inside. That just makes sense. So if you look up 0.02 in the body here, 0.02, the closest I can get is 0.0202, which is a z-score of negative 2.05. I like it, negative 2.05.
Can you explain one more time how you got that?
Yeah, so I want to be 96% confident, which means I want to catch 96% of the data. The z-score chart does not understand areas in the middle. It only understands areas below. So how do I find this z-score? Well, what area is below it? If there's 96% inside, there's 4% outside, which means there's 2% on this one side. And then I look up that 2%, and that's how we found the negative 205. Is that all right?
Yes,
So
thank you.
yeah, if I wanted to be 73% confident, ooh, I like that number, 73% confident, what area is down here?
0.135.
Yes, 13.5%. There's 27% outside. And if you cut that in half, that's 13.5. So I would look up 0.135 in the z-score chart and get my z-score, blah, blah, blah. Yakety schmackety. All right. Let me move that out and get out of here. Go away. All right, so now we have everything we need. Go away. Okay. We have everything we need for this formula. I know my p hat, 70.4%, so 0.704. And that's my best guess for what it really is. And then I say, give or take 2.05. I shouldn't have put the negative there, but too bad for me. Times the square root of 0.704 times 0.296 divided by n, which was 652. Okay, now this is an adventure to get into the calculator correctly. So I'm going to let you guys try to get this error, and then I'll see if anybody needs me to show them how to get this in the old calculator. Somebody's screaming. Hopefully everything's all right. Does anybody have an attempted answer for that, for what the error is?
0.741.
Let me see. It's not what I got.
I got 0.037.
7, yeah.
0.705.
Oh, I see. All right. I think you guys are bringing this in. Here's the error.
Oh,
Yeah. Because I only want to have to put all that shit in once. So I don't want to do 0.704 minus all that shit and then 0.704 plus all that shit. In fact, here, let me go ahead and show you guys a couple of shortcuts on the calculator. All right, I'm going to stop sharing. Where are you at? There you are. Okay, wake up. As we all wait for this to wake up, here it slowly comes. There it is. All right, hold on. Let me share this bad boy. All right, now what really sucks for me is I need to be able to see, not that, this. Put that over there. Oh my God. Okay. So now watch this. This is kind of cool. So 2.05 times the square root. What was it? 0.704 times 0.296 divided by 652. So this is for those of you that have the older calculator where it doesn't. So some of you guys have the square root symbol get bigger and bigger and bigger, right? Did I do times? Good job, Jeff. Divided by. All right. So the square root symbol. So I gotta, if you have an older calculator where it doesn't have a bigger square root symbol, it just has a square with a parenthesis. Do not close the parenthesis until you get all the stuff in there that needs to be in the square root. Are you guys with me? So if you hit enter, you get that. Now, if you round that to a whole percent, what do you get?
4%.
4%. And isn't that, I mean, if you've ever seen this anywhere, it's either 3 or 4% that you see, because it's sort of like the 652 is kind of like a normal kind of survey size, somewhere from 600 to 1300, somewhere in there. So you almost always see this plus or minus 3 or plus or minus 4 at the bottom of the article or whatever. I have no idea if you guys, I have no idea how you guys access news now, and that makes me very concerned, right? I know most of you guys are in the age group where Facebook is for old people, so I'm pretty sure you're not affected by Russian bots on Facebook, which is good. But then there's other horrible places to get news. But has anybody ever seen what I'm talking about? The plus or minus 3 or the plus or minus 4 at the bottom of the thingamajig? Has anyone ever seen that? Or do you all have like, that's old man shit, Jeff. That's that's you and your newspaper. You get a newspaper, Jeff? I do, actually. I do. They still exist. Okay, now let me show you the really cool thing. I still have to add and subtract this dumb thing from whatever it was. I forgot. 0.704. Where'd it go? Yes. So this is nothing major. You can do this without doing what I'm about to do, but let me just show you. This is, I can't remember if I've shown you this, but you guys see this button right there? This button right there, it's called stow. Stowaway. I want to store. So if I store this in X right there, store it in X, watch what I can do now. 0.704. No, Jeff, try it. There you go, buddy. Minus X. Bam. No, Jeff, you can't do that. Oh, goodness. And then 0.704. God, I feel like I'm Joe Biden. Plus X. Bam. I like Joe, but it's a good thing he's surrounding himself with people that know how things work. Anyway, so there I am subtracting that business and adding that business without actually having to deal with that business. It's always nice. So you can use that little store thing if you want to. You don't have to. Did you guys get that answer a different way? I'm sure some of you guys already got it. But it's just there for you if you want to use that. Are you guys with me? So let's go back to the handout and let's see how to put that down and what that means. Oh shit, let me move this over. Go over there. Holy shit, come with me. There you go. Now I gotta find you guys again and I gotta share. And yes, I do have to say it as I do it. It's just the way it is. All right. So right here, I can put down here 0.0366, blah, it doesn't really matter. So then when I do this, I get from 0.667, right, to 0.741. So I want your confidence interval numbers have to be at least as many places as this guy was. Does that make sense out there? All right. Is that cool? Any questions from that, guys? Okay. So then the conclusion, yes, you still have to write the conclusion. We are 96% confident. You guys take a minute and see if you can finish that out. Don't say it out loud, just try to finish it yourself. Finish it. All right, let's see. So we're 96% confident that the interval. Now here's where things get interesting. I'm curious what you guys put down here, but you always have to have units. And the units for this is percentage. So change these into percentages. That the interval 66.7% to 74.1% contains the true percent of, I forgot what this was about, people that voted in the last election. So it's very, very familiar. It's very similar feel to the confidence intervals for the mean that we did last time. It sounds a lot the same. The work feels kind of the same. It's just that the check is different. It's not just n greater than 30 anymore. That's not good enough. And of course, the formula is a little different because we're talking about percentages. What will often happen is the problem is a percentage problem, and people will get here and say, I can't do it because I don't know the standard deviation. Of course you don't. You're never going to know a standard deviation for this because it's built off of NP and Q. I don't need to be told a standard deviation for a percentage problem. You guys okay out there? You guys, what's happening? All right, I see somebody unmuted for a second, but I guess you're okay. Okay. All right, so that's that one. So that's much more informative. If somebody said to me, you have about an 80% chance of passing this class, you're like, all right. But if they said you have somewhere between a 60 and 100% chance, you're like, what the shit good are you? You don't even know. Do you understand what I'm saying? So isn't 60 to 100, isn't the middle of that 80? Right? So if they say you have an 80% chance, I'm like, all right, can you tell me a little more? Somewhere between a 60 and 100, it's like you're useless to me, right? So getting this extra information, don't just give me the 70.4%. Give me this interval. That tells me a few things at once. It tells me what the middle is, what you got, the 70.4% is right in the middle, and it tells me how confident you are about that finding. Okay, maybe. All right, so here's where things get even more interesting. Do you guys remember last time? Let me bring this back up here. We did this problem with the dolphins thing, right? We actually created this formula. This formula right here, we created it. from the error part of the main formula. So we can do a very similar thing with this. Here's the error part of the percentage formula. If I solve this for n, I'll spare you that. Just use a bunch of good old algebra. Algebra saves our ass all the damn time. I will end up with this. So what this means is if I know what I want my error to be, I can figure out how large of a sample I need. And then I can see if it's possible. If I need to talk to 30 people, sweet. If I need to talk to 3 billion people, no. So look at part A. Can somebody just pick out for me in part A what the error is that I want?
.03.
Yes, I want to be within 3%, and I love it. 0.03. Don't use 3. 3% is the number 0.03. So we always use the number. How am I going to figure out what Z is? What part of that's going to tell me what Z is?
The confidence level.
Yeah. Let me just open something up there. And I want to be 99% confident. So if I look at my little baby chart down here, 99% confident is a Z-score of 2.575. You guys see that? All right, what's going on? Why are you? There you go. Okay. So let me come back to this. So I know Z is 2.575. And doesn't this make sense? If I want to be more and more confident, doesn't Z go up? The more confident I want to be, the further away from the mean I've got to go to catch more stuff. So my Z score is going to get bigger. Doesn't that make N get bigger? And doesn't that agree with everything we know about what makes somebody more confident about something? You take a larger sample? Maybe? No? No? Okay. So now all I got to do, what is your best guess? Do we have a clue what the shit these are? I know what E is. Check. I know what Z is. Check. What are P hat and Q hat? We don't know. We don't have a clue. So what's your best guess? If you had no idea what percentage of the class likes lima beans, what would be your best guess?
Half.
Yes, half. It's your best guess, right? I don't know if that makes sense to you guys. Even a little, stay with me now. Stay with me now. I can sense this, and I have no idea if this sense is correct. This is me just making shit up in my head, but stay with me. All right. So my best guess is 50. Sort of like the example I used to give is pretend like we're in a classroom. And I said, what percentage of the people in the next classroom are women? Well, best guess is 50%. Here's something even better. Let's see if you guys like this. If there is something I'm not sure about in my problem, in this case, I don't know what P hat and Q hat are. Should that make me take more of a sample size or less of a sample size? If there is something I'm not sure about, should I have to take more people or less people?
More.
Yeah, I kind of have to penalize myself. Anytime there's something we don't know in statistics, the math is going to kind of penalize me for that, which makes sense. We want to be more conservative. So mathematically, if I assume P hat and Q hat to be 50-50, 50% each, that makes N the biggest it could be, which, of course, because I have no idea what they are, I should be penalized the most. I should have to take more people. So let's see what we get mathematically here. So if we throw everything in, so we're going to assume that P hat equals Q hat equals 0.5 because we don't know what they are. So let's see what we get for N. So I got 2.7. You can do it. What I just wrote times 0.5 times 0.5 divided by 0.03 squared. And for some reason, people always forget the squares. So let's see what we get. Okay, I did that fast. I don't know. Let's see if that works. What do you guys get for that?
1841.84.
Yeah, 1841. Sounds like a history quiz. So we always have to take that and round up because I don't want to chop people up into little tiny 0.84 bits. So let's round up to whole people, right? I don't want to create a bunch of little Dexters running around. Now, part B is the same problem, but now I know you guys have heard of preliminary studies. I'm pretty certain you've heard that word before. You do a preliminary study. Very small group. I took 42 stat students and I found 31 of them passed the first time around because that's the whole point of this problem, right? So now the difference from the first problem, hello, give me a minute, kids. All right. The difference from the first problem is that I now I know what p hat is. How do I figure out what p hat is from this preliminary study I did?
X divided by n.
Yeah, so 31 out of 42.
0.738.
0.738? All right. I'm going to trust you. I don't see anybody saying otherwise. So then what's Q hat? You're like, why should I talk? You're going to get done eventually, Jeff.
262.
Yes, I like it. Cool. Thank you. So the only difference in the formula now is instead of assuming they were 50-50, I can actually put in what they are, what I found from my preliminary study. So if I put those in, so 2.575, I still want to be 99% confident. But now I do times 0.738 times 0.262. I don't do 50-50. Divided by, I still want to be within 3%. Let's see what we get this time.
$14.24.52.
Yeah, I like it. Point stuff. So each rounded to 1425. Almost 400 less of a sample that I have to take. That's why preliminary studies are done, to get a little bit of a feel for what things really are, and that can inform me how big of a sample. Instead of just taking that many people, this doesn't seem like a lot less, but it's almost it's over 400 people less, right? That'll take a lot less time. That'll be good. Anyway, all right. So that's one reason why we do preliminary studies. That's one very specific reason why. There's other reasons why, but this is a good reason. All right. Let's do one more example, and then we'll do a little bit out of, we'll talk about T-scores. I kind of teased those before. So I'm going to stop sharing. Does everybody finish copying from up here? Okay. Here we go. I'm going to stop and see if anybody yells at me. Oh. 0366. Oh, that's from earlier. All right. So this is kind of nifty. I love this because you actually, it feels like you don't get enough information for these because they don't have to tell you a lot. So I'm just going to tell you this. We find 48 people out of a sample of 811 that enjoy political ads. Right, so find the 90, let's just make it, 90% confidence interval for the true percent of all people that like political ads, right? So be sure so let me give you a little bit of a structure. Find P hat and Q hat. Check NP hat and NQ hat, and then make the confidence interval. Blah, 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 blah. All right, so you guys work on that. I'll take a union break. Put my head somewhere nice. There we go. That's weird. Huh. All right. Interesting. Sorry. Wow. Oh, that's right. All right. I'm going to catch up to you guys a little bit. So let's see. P hat would be 48 out of 811. What do you guys get for that?
0.059.
059.
059, yeah. Q hat is going to be 1 minus 0.059, which is 0.941. NP hat will be 48. And here, and again, you could either do 0.059 times 811, but look here, isn't 0.059 times 811 going to be about 48? You can see that. You can see that. That times that is going to be about that. Why do I say about that? Because that's rounded. And you can tell me if that's true. If you did it, then you get about 48. And then NQ hat is going to be the rest, which is 763, right? Did you guys get roughly 763?
Yep.
Yeah.
Okay. So you can either do the long way or the short way. It don't matter. Oh man, I got to recharge my poor little battery on my calculator. All right, so now I've left myself with 0 room for the confidence interval. But just to remind you guys, it's P hat, give or take, Z square root of P hat, Q hat over N. What did somebody get for Z? For the 90%?
1.645.
Yeah, so if you look in your little baby chart, you'll get 1.645. So I've got P hat 0.059, give or take 1.645 times the square root of 0.059 times 0.941 divided by 811. Oh my goodness. I guess I could have used that space over there. I'll take this over here. So that's 0.059, give or take. Let's see what the error is. When you do this, make sure all of this is in the square root, right? That's where people make some mistakes. All of this has got to be in the square root. So I get 0.014 roughly. Like 0136 blah, blah, blah. Is that what you guys get?
Yeah.
Okay. And then if I do 0.059 minus that and 0.059 plus that, I get 0.045 up to 0.073. Nifty. So that's my interval. And now I have to write that conclusion to explain what the heck that means. This is different. I think I see parents walking in the background of something. I normally don't have to deal with them at all. And now they're out there. Oh, all right. Hey, parents. All right. So I'm going to erase this top part so I can write my conclusion. So in conclusion, we are 90% confident that what?
The interval.
Yeah, the interval.
4.5%.
Yeah, 4.5% to
7.3%.
yeah, contains the true percentage People who like political ads. Sounds high. You know, if I ran for office, the only ad I would put is say, I'm Jeff Waller. Just wanted to remind you, I'm not putting any ads out there except this. Take care, everybody. And then you know, people would still vote against me, but I'll do what I can. So it has a very familiar feel to it. And it's just like what we did with the X bar stuff. It's very similar. Oh, thank you. Somebody would vote for me. I would get 2 votes, maybe 3 if my mom would go vote. All right. So let's do let's do a little bit more, and then we'll call it a day. I'm not going to keep us here too long. And this next part is related to Guinness beer. Guinness. I don't personally like Guinness. Anybody like Guinness out there? You know, if you're legally allowed to drink. Don't tell me if you're.
It's good in an Irish car bomb.
There you go. There you go. That might make it more interesting for me. Guinness itself, I'm not into. Yeah, when I was in grad school. Oh, I'm sorry. Let me not do one of my stupid stories. Somebody's got a real question. How did you find Z for this problem? Oh, yeah. So it was 90% confident, right? So if I look at, you can do this one of 2 ways. Everybody's very happy that you asked the question and spared them from one of my stories. So if you look at the positive Z-score chart, you can look at the little baby chart in the corner. See there, 90% confidence is 1.645. Or if I'm 90% confident, there's 10% outside, which means there's 0.05 below. If you look up 0.05, it's one of the star dudes, which takes you down to 1.645. So either way you look at it, you find 1.645. Is that all right? No? Oh, no, not the Guinness Book of World Records. No. There's probably a world record related to the Guinness that I'm talking about in the Guinness that you're talking about, but yeah. The most, anyway, all right. What's the plural of Guinness? It sounds Guinnesses or Guinea? I think it's Guinea. Okay. Sure. Thank you for that. All right. All right. So what does any of this have to do with Guinness? I will get into that right now. The one kind of problem we haven't looked at yet involves what if I don't know the population standard deviation. So just to remind you guys, is anybody still copying this? My big old head in the way? You guys all have this thing? All right, I'm going to take it away. So just to remind you, what have we got so far? We've got 2 of the 3. There's going to be a total of 3 confidence interval formulas. This is the first one we talked about. And notice how we have to know the population standard deviation to use this. Then we just did this one. And now we're going to do the one that what if I want to find a confidence interval for a mean, but I don't know sigma? What did we say? What did I say earlier today? And which is basically true throughout all statistics. If there's something you don't know in a problem, you have to penalize yourself somehow. You have to make things worse. You have to take a bigger sample or something's going to happen. So here's what happens. if there's something I am not sure about, should that lead to a larger interval or a smaller interval? Which one?
A larger one.
Larger.
Yes.
Larger, more room for error.
Yes. And it's kind of funny I haven't said this yet, but I got to make it bigger to cover my ass for what I don't know. Right? Does that make sense? So if I don't know something, my interval's got to get bigger to cover me for that fact. So I used to like to say, so remember the fish net, right? So if I know the fish, if I am not sure how wide the fish swims, I'm gonna have to throw a larger net out to cover for that. So that if I don't know what the spread really is, my interval has to end up being bigger. So all that there, we got that whole idea there. So what changes is, this is interesting. I'm going to find a sample, which means I'm going to take a sample size. I'm going to find a standard. This time I'm going to find an S because I don't know this. So these things can't like change. I'm going to find this and this from my sample of size N. So the only thing that I can change is this. So instead of using a z-score, we're going to use a t-score. That's exciting. That doesn't mean shit. But so here's what it is. If the z-score for a situation would be like 1.96, the t-score could be like 2.87 or 2.39. It's always going to be bigger to force my interval to be bigger, to make my error larger. Why does that make sense? Because there's something I don't know. I'm using an estimate. S is an estimate for sigma. It's my best guess for sigma because that's all I got is what I see in the sample. All right, maybe. And here's the connection with Guinness, right? I'm not going to suddenly pick up a Guinness. Here's the connection. I don't like Guinness. The guy who created this, his name was William Gossett, and he worked in the Guinness brewery. And it was a part of his contract that any research he did would be owned by Guinness. So he did research on this. He created this because he knew the problem with not knowing this. So he created this distribution. And when he submitted it to this journal article, he used a different name. He called himself Student. So you might see the phrase students t-scores because it's his pen name. It's what he used instead of anonymous. He called himself Student so that he wouldn't have to give his research to the brewery. So I don't have a clue if that's interesting to you or not, but I always like to tell the story because it's kind of nifty.
Is that an S?
There, yes. I was trying to make a really good S. Huh?
What does it mean?
Uh-oh. What does sigma mean?
The amount of standard deviations from the
No,
mean?
just what is it? Don't tell me what the definition is. Just tell me what it is. Like mu is what? What's mu and what's x bar?
The sample and the population?
Yeah, means, right? So sigma is the population standard deviation. What's S?
Okay.
Sample standard deviation. Yeah, let's not forget
Got you.
those. I like it. So if I don't know what the population standard deviation is, and I'm going to take a sample anyway, I might as well figure out the sample standard deviation because then at least I have something to put here. But then this is always a little bigger than the Z would have been to cover my ass for not knowing what this really is. All right, now, here comes a seemingly completely unrelated thing. Is everybody decent with that? Do you guys get the idea of this at least? Why it's got to be there? Hopefully you do, because I don't know how else to say that. Here comes something that seems completely unrelated. If I told you I have 3 numbers and they average to be 80, Do you know anything about the three numbers?
They add up to 80 when divided by 3.
So they actually add up to be what then?
140.
240, 11. So you don't know anything about the individual numbers, but you know they add to 240. If anyone's not sure why, that's the only sum that when you divide it by 3, you get 80. That's why. So what's that got to do with shit, Jeff? Well, just give me a minute. Geez, calm down. Oh, sorry. It's whatever the imaginary student is I'm talking to. I can make up, I can totally make up this first one. Not even have to have a care in the world. Let me make that 20. Woohoo! And I can make that, let me make that 150. Woohoo! Right? But now, can I just make that last one up? Can I make the last one be anything I want it to be and still make the average 80?
No, it has to be
70.
70.
70. It must be 70. So I could have made this anything, right? I could have made it negative 18 billion. I could have made it any damn thing I want. And then this one, I could make that one anything. But the minute I get to the third number, it's the one that makes things work. So if I ask you, I have my n is 3 here, right? N is 3. How much freedom do I have? Do I have 3 full degrees of freedom? No, I've only got 2. Does that make sense? 2 like degrees of freedom. It's sort of like how we measure things. And I'm going to say it like it's from Braveheart. Degrees of freedom. You can take away my stuff. So degrees of freedom is always n minus 1 because no matter how long the list is, it's the last number that isn't free to be anything. So what's that got to do with anything, Jeff? I don't know. So let me make sure this, let me come back to this then. The reason I talk about this is because it's on the chart we're going to use. Plus, it's a very important idea. Let me ask you, when am I going to be more sure about this? When is this going to approach that? When do I feel better about this? What's got to happen for me to feel better about this, the sample standard deviation? When would I not trust it at all? What would be true for me to not really trust it much?
Less than 5.
Okay, I like it. You don't have to be that specific. A very small sample, I'm not going to trust it that much. But the minute my sample gets really big, right? If I'm talking about 1,000, 2,000, I'm feeling pretty good about that. Are you guys semi with me? If I only talk to 3 people and I get a standard deviation for that and say that represents America, it's like, what? But if I take a larger and larger sample, I'm more and more certain about this approximating that. Is that cool? Which means the t-score's job is more needed when my sample size is small. If my sample size gets bigger, this is going to get closer to the z-score because it's not needed as much anymore. It doesn't have to cover my ass so as much if I'm pretty sure about this. So let's look at the chart. Oh my goodness, Jeff. Let's look at this t-score chart. I think did I put it up on the, I might not have because I'm a jackass. Let me see if I did.
Yeah, I think I saw it up there.
Oh, it is? Cool. Maybe I'm not as big of a jackass as I thought. Unit 8. Yes, cool. It's there. All right. Good job, Past Jeff. So here it is in Unit 8. There's the t-score chart. All right, so just want to show you where it is. I'm going to open it better so I can see it better. That's exciting looking. Sorry. Let me stop that. Let me share it in a better way. Where did it go? There it is. Oh shit, that's the wrong thing. Where'd you go? There you are. Why is everything blue? This is weird. All right, hold on. There it is. Why are you over here now? Oh, I see, because I shared the wrong thing. All right, give me a, sorry, guys. Oh, Jesus, where are you? I thought that was you. That is you, so why? Don't you dare. There we go. Okay, okay. Now. Let me ask you a couple things. What if n is 11? What will the degrees of freedom be?
10.
10. It's amazing. Degrees of freedom is always n minus 1. So do you see over here? If your n is 11, do not go to the 11th spot. That's wrong. You want to go to the 10th spot. Now, stay with me. This is, all right, it's going to take a little getting used to. This chart is definitely different than we're used to. See the top? There's 2 freaking rows. Area in one tail, area in 2 tails. When we get to chapter 9, this is really, really going to make a lot of sense, and we're going to be thankful that they made the chart look like this. Right now, you just got 2 options. So for example, if I want to be 90% confident, what area is into the tails? Do you see why we call them tails? Because they look like freaking tails. So what area is in the 2 tails?
0.05,
That's in 1 tail. In 2 tails, there's
0.10.
10%. So in 2 tails, there's 10%. See, that's in 2 tails, there's 10%. And in 1 tail, there would be 5%. Am I not in the same column, no matter which way you look at it? Are you guys with me? 90% confidence will have 10% in the 2 tails, right? So that's this column, 10%, 2 tails. But what if you look at it like it's 5% in 1 tail? Oh, 5% in 1 tail, same column. So if I want to be 90% confident and my degrees of freedom are 10, I'm going to go to this column and I'm going to stop at 10. That would be my t-score that I would use. So the t for the situation would be 1.812. Now, can somebody take a second? Does somebody remember? We just did a 90% one not too long ago. What was the z-score for 90%?
1.645.
Yeah. Is the t-score doing its job? Yes, it's a little bit bigger than the z-score would be. So it makes my confidence interval a little wider than it would have been to cover my ass for not knowing the real standard deviation. Also notice that as my sample size and thus my degrees of freedom get larger, what happens to the t-scores?
Smaller.
They get smaller and smaller. In fact, look at the very last entry on this table. 50, 60, 70, 100, 150, 2,000. I love that. So when your sample gets large, do these look familiar at all? Maybe even this one. This is off by a number, but that's because it's actually more precise. Don't these look like, aren't these z-scores? There's the 1.645, right? This is the first day we're using this thing. I understand. And we're about to do some more examples to make sure we can all read this crazy ass chart. But what's really beautiful is if you look at the last row, you'll find z-scores. So watch this. If I have to make an 80% confidence interval, which column am I going to look at? See who sees how to use this thing. 80%.
Last column.
Sorry. Yeah, the last column, right? I'm going to look at the last column. And what if I know sigma? What if I know sigma? and it's normal. That means I want to use a z-score. So I can still use the t-score chart. I just go all the way to the bottom. That would be the z-score I would use, 1.282. So what I like to say is, if you use the t-score chart, if you stop, you get a t-score. If you go all the way to the bottom, you get a z-score. Bless you. Ain't no party like a z-score party. Because the z-score party doesn't stop. So if you stop, you'll get a t-score. If you go all the way to the bottom, you'll get a z-score. That is kind of useful. You don't realize that fully yet. In fact, you probably hate this chart at the moment. I'm sorry. So let's do this. Where do I have this thing? Another thing up on the, there we go. Up on Canvas right now in that same place is this. What time is it? All right, I'm going to let us out here very soon. I just want to do these first three, I think. So if n is 6, and we're assuming it's a normal distribution with S known, but not sigma, n is 6, 99% confidence. Take a minute and figure out the degrees of freedom and then figure out the t-score. N is 6, 99% confidence. Wish there was a quicker way to erase this shit. All right. Get out of there. Get out of there. All right, that's fine. So just write this down. You can't write with an eraser, Jeff. N is 6. What did I just say? Gosh. 99% confidence. So, of course, what's the degrees of freedom?
5.
That's crazy. And then somebody else tell me 99% confidence. Which column am I going to look at?
The first one.
Yeah, because I want 1% in 2 tails. So I always look at this row for confidence intervals because it's just 1 minus this, you know, 100 minus that. So I'm going to use this column. I'm going to stop at 5. So that must be my t-score I would use. Now that is big, isn't it? Are you guys at the point where you realize that's freaking big? That's 4 standard deviations. Why is it so big? Because the sample's so freaking small. If I take such a small sample, I'm not going to be sure about shit. So this is going to have a lot of ass covering to do. That's why it's so big. All right, I like it. So try the next one out. I don't know if you guys are able. Go ahead and write this down. I don't know if anybody's relying on my sharing of the screen. So N is 101, 90% confident. You wouldn't be able to see it here anyway. Too bad. Just hopefully you can access your t-scores. So obviously here, the degrees of freedom would be 100. It's always 1 less. 90% confident. Which column am I going to use?
The 4th column.
Yeah, so 90% means there's 10% outside in the 2 tails. So I'm going to use this 4th column. So I'm going to just stop. I already forgot. 100, right? I'm going to stop at 100. And I see this. 1.660. So at 100, it's already getting pretty close to what the z-score would be. So 1.660.
So what if your degrees of freedom is like 125?
You always, so to be more conservative, always, if my degrees of freedom was somewhere between 100 and 200, I would use 100. And, you know, whatever confidence level I want, right? So if on this problem we just did, if it was 187, I would use this. My degrees of freedom would be 186, which is not on the chart. So I would go down to the next one. I make it worse for myself for not knowing something. Does that make sense? If the degrees of freedom was like 199 or something, or 197 even, you could use this. That's close enough. But anything else, you're going to go to the next one up. Because again, anytime there's something I don't know, I'm going to penalize myself a little bit. Now, would technology be able to give me a much more precise t-score? Yeah, of course. So when you're out in the real world building bridges and shit, I want you using technology. Right now, you ain't doing that. So I don't want you doing that. I want you doing this because I'm crazy. All right. Let me come back here.
So I had a question.
Yes.
So for C, we would use 90 since it's 93.
There you go. I love it. So the degrees of freedom is technically 92, but because you have some weird ass old Jeff dude teaching this course, you're going to use 90. So if you go to 90, oh, I'm sorry, which column do we want? 98% confidence. So which column am I going to use?
Second column.
Yeah, because 2% outside then. So you go down to 90 and you get the 2.368. You guys with me? So your level of confidence tells you which column to look at. And then your degrees of freedom tells you where to stop. I like it. And just, I want you guys, I do have a problem down here. We're not going to make it there today, but I did say we were just going to do this first part, didn't I? That's all right. I'll keep this part for next time. When we get to the point where we actually start doing problems, it's going to be simply, instead of putting a z-score here, you just use the t-score chart. You put that number there. So it's not, functionally, it's not very much different. So if I did this equation and I looked up the z-score, and if I have to use this equation, I'm just going to look up the t-score on the t-score chart and put it there, and it doesn't change anything besides that. Does that make sense? So can somebody tell me why were t-scores invented? For situations where what?
Samples are small.
Sigma is unknown.
Yeah, sigma is unknown. It really isn't anything to do with the sample size. It isn't. The t-score does get smaller as the sample gets bigger, but why were t-scores invented? For when I need help with grammar, for when we don't know sigma. In fact, the formulas give it away. This is the last thing I'll say, I think. Get out of there. So there's the formula for T stuff, right? And the formula for Z stuff looks like this. So what goes with S? T. What goes with sigma? Z. And then the last thing I'll say is they both require a normal distribution. So you have to know it's normal to do either one of these things. Let me see, I got a chat. Can you repeat what you said about what degrees of freedom level confidence means for the chart? So in the chart, degrees of freedom, so level of confidence tells me which column to look at, right? So if I want to be 99% confident, I'm going to use the first column because that's 1% outside, 99% inside, 1% in two tails. So the confidence tells you which column to look at, and the degrees of freedom tells me where to stop. So if I have 22 degrees of freedom, I would use this. But if I had 30 degrees of freedom, I would use this. Is that cool? And again, this is the first day you've ever seen this chart. I'm almost certain for most of you guys. So you got to let it sink in a little bit. Okay. Otherwise, oh. Okay, cool. Otherwise, I think that's plenty for today. Because I want it to be nah. So let me know if you need to hang out, if you have any questions. Otherwise, you are free to log out.
One of those problems say not normal. Are we going to get into that next week?
Yeah, for example, this one, why is this one okay? What saves this guy's ass?
And is greater than 30.
And is greater than 30. This one, is his ass saved?
No.
No. So this is the one problem in these four that we would not be able to do. You could not do this problem. Even though I know sigma, so Z is like waiting to be used, but it's not normal, and the N isn't big enough. Oh shit, everything died, right? Is that cool?
So we would just say like cannot do problem or something like
Cannot
that.
do it. Exactly. This is something we would do. There's actually a process you could use that you would learn if we had a stats 2 class, but we don't have a stats 2 class, so too bad.
Alrighty, thank you.
You're welcome. Everybody else all right? All right, I'm gonna head out. I'll see you guys. Take care. Vote. Okay.